runtime with the GPU available to us, right? So let's do this. Let's change the runtime, and it should reset if you haven't already. For those of you who are using Google Colab Pro, you get access to these wonderful V100s and P100s, like Turing architecture onwards with tensor cores. And can I also get a sense of, sorry, I disconnected and can't see the link. That's okay, I can send you that, no problem whatsoever. There you go. How's that?
Can you show how to change the GPU thing again? Sorry.
Okay, yeah, no problem. So maybe what I will do is just explain a little bit then. For those of you who are using Colab for the first time, if we just click on change runtime type here at this little toolbar, and then the hardware accelerator, you'll see that there's a tensor processing unit available to you now, which is awesome. Graphics processing unit and none. Let's go for a classic GPU, right? And don't worry about this if you're on standard Colab. It'll just be great. Thanks, WeCloudData.
If I don't have GPU, should I just choose none? This is my personal computer.
Oh, if you're using, sorry, go ahead and say that again.
This is just personal computer, so I don't have GPU. Should I select none?
Oh yeah, yeah. If you don't have a GPU, if you are you not able to access Google Collaboratory?
I load it, but is that on the cloud?
Yeah. So if you follow that link, if you have a Google Drive account, is that a thing? Are you able to access Google?
Yes, I can access the Colab. Thank you.
Cool. Yeah, no problem. And then if you should have a GPU available to you. Google were generous enough to kind of offer Tesla K80s subject to availability to free users, which is wonderful. I realize I'm talking at this and not the camera, so I do apologize for that there, guys. Yeah.
You're on mute again.
I do apologize. We all got muted there. Okay.
Okay.
Anyway, everybody should be set up at this point. I will, considering then what we're seeing with people's knowledge of Colab, I will talk quickly about, and maybe someone else can speak up about it, considering we're talking about deep learning here and we're going to get involved in TensorFlow. Can anyone tell me why we would be using a graphics card? Why do we need a graphics card in this situation? What's going on? Anybody know?
Fair, it makes the computation run faster than the normal CPU.
Yeah, for sure. I nail on the head there. That's exactly it. The quick history of it is GPU has a lot of cores. Yeah, exactly. And they're proper specialist cores as well. They started off right as these single instruction, multiple data powerhouses back in the days. And, they were developed for video games. So they were doing lots of similar processes like translation vectors, like moving NPCs and objects very quickly and then rasterizing them on your screen. So they were developed to do lots of kind of matrix multiplication based operations, and it quickly became apparent that they could actually be adapted to deep learning because there is a lot of, dot products and matrix multiplication involved. Nowadays, right now, since the last decade or so, they've become really, really specialist. And now we're working in Colab or in the cloud, or if you're lucky to have it at home, you might have Turing architecture onwards NVIDIA cards, and they'll have specialist tensor cores, They'll have mixed precision cores that speed up the operation even further. So we're in the future right now, and deep learning has really benefited from these hardware advancements, just to give you a kind of little insight as to why we're bothering with it. So let's move on. Let's install our dependencies. These are not massively important, but if you double click on this little cell here, you'll notice that I'm installing Cora, because we're going to look at a video later. And we're installing Seaborn just for some nice visualizations. And we're installing TensorFlow Hub, which we'll look at later on. And the reason I'm talking about TensorFlow Hub, if you give me a sip of tea a second, is that I'm really excited about the TensorFlow ecosystem in general. It's becoming much more than just what was happening in TensorFlow 1. It's becoming this readily deployable. There are lots of moving machine parts that you can bring in and out. And we will look at that later. There's TF agents for reinforcement learning now, and there's the TensorFlow object detection API, which we'll be looking at in the next session. I'm really excited about that. So I kind of want to push you towards drumming up to the excitement of that. So let's install that. I'm hoping that you guys are all installed at this point, and I'm going to mount this so I can show you guys some crazy 3D visualizations of images later, because we're going to look a little bit at convolutional neural networks. So if you bear me 1 second, I'm just going to, hopefully my computer sorts itself out and I can click on this. I'm going to authorize. Okay, so I'm going to run this cell now. We should all be running a GPU now, and TensorFlow 2 will automatically just recognize that you're using a graphics card. Right now in Colab and in general, it's all migrated to TensorFlow 2. So if you do need to go back to backwards compatibility, you're going to have to switch. I work a lot with the kind of the TensorFlow 1 iterations and stuff, just because of different plugins I'm using with deployment and so on. But we'll talk about that later. You can see I was looking at a nightly as well. So you're welcome to look at the nightly bleeding edge deployments that are coming in. They're getting a lot faster. They're always working on this stuff. We won't so much be looking at, we'll look a little bit at the low level stuff in terms of being able to automatically create graphs now, but we're generally going to stay high level with Keras. Oh yeah, so just Chai, so just to go back on that, mounting a drive, all I'm doing is I'm just mounting some images to show you guys how to plot images in 3D, just so we can see cool properties. So you don't necessarily have to do that, because I'm going to show that to you anyway, and you can do that in your own time. So don't worry too much about that. So what was I saying? Yeah, bleeding edge deployment. Let's actually just move on. So let's actually just check that our graphics card's available to us, and we can verify that in lots and lots of different ways. One of them is with the tfconfig experimental method. So if you run this, you should get true if you're running your graphics card. If not, go back to this step. For those of you who use graphics cards a lot locally, you'll recognize NVIDIA SMI, right? So you can get all your information. You'll see I've got a Tesla V100 available to me, super fast, a proper data center workhorse. So you'll be using this a lot if you're on a local machine in the future. I mean, NVIDIA isn't the only company out there, but they've become the kind of go-to for things like CUDA and all those other languages that we're building parallel computation on top of. There's a little bit more here about this that you can go back to whenever you want, but I'm going to move on, and I'm going to, how many of you have experienced or know about deep learning at this point? What is deep learning to you guys? Can anyone speak up about that? What does that mean to you? The term is thrown out there a lot now, isn't it? It's everyone's always like deep learning this and deep learning that, deep learning optimize this, and it's all in your phones. Sorry, go ahead.
So what I understand is deep learning transforms the original data through various layers to find the decision boundary, and it needs huge amount of data. Otherwise, such a complex model would definitely overfit. That's what I understand in 2 lines.
For sure, I mean, that's great paraphrasing. I love it, and Ashton as well has hit the nail on the head with the deep part, with more than one hidden layer, right? We're going to start to look at things like shallow MLPs with just one hidden layer, but yeah, generally deep learning, we're talking about depth. We're talking about really deep structures and architectures. So for sure, and you do need a lot of data because they are really complex, because they're great approximators, they're great function approximators. We can solve a lot of problems with neural networks. Traditional machine learning, you go for specific models or specific algorithms for specific problems, right? With neural networks, we can solve a whole lot of problems by just switching different layers and switching different parts. And we'll see that. So basically what we're doing is we're mapping an input to an output and we're just looking for the right parameters to do that with. So it could be mapping an X to a class, or it could be mapping a spectrogram to a sentence, a spectrogram being someone's voice recorded, you know, with a bidirectional recurrent neural network. There are lots of ways of using these things, but I'm going to start off with the proper building block from the 50s. And I'm always talking about these guys. Does anyone know what I mean by the perceptron? And does anyone know when it came about? What was the story? Where, like, who was talking about perceptrons? Was it like the 90s? Because it wasn't, it was the 50s. Sorry, go ahead.
I believe this was,
I think if you're 40,
I believe it was the 60s.
Yeah, it was like late 50s, 60s, right? And they were super excited about the perceptron. They were, if you look back at the videos, I urge you guys to Google it. There's videos of these guys talking about perceptrons like taking over planets and marrying perceptrons in like a really tongue in the cheek way. But they were, yeah, exactly. Rosenblatt for sure. That's exactly who. So it's good that you guys know this. But the reason I'm talking about the perceptron is that was the beginning of the excitement about this kind of buzz of what potentially could be deep learning, the kind of proto deep learning connectionist school stuff. But there was a problem, and the problem came about once we started thinking about nonlinear data, because what this is a binary linear classifier, right? So we're talking about weighted inputs and then an activation function, right? And we're talking about the heave side activation function. So if you run this, the heave side activation function is super simple. It's not going to do much for us except, bear with me 1 second. So if I just put 1 in, -1. Oh, I gotta actually run my function or define my function. I get 0, right? So if I put anything above, I get 1, binary classifier. Now, can anyone tell me what these are? We're going proper comp sci 101 before we really expand out to kind of modern deep learning. What are these in terms of computer science 101? These are logic gates. Classic problem, right? Classic thought experiment, and you know, actual gates that we use in the real world in computer science right now. So we've got or, we've got and we've got exclusive or. Now I'm talking about exclusive or is because exclusive or was the real dagger that made people kind of gave us our little pre-AI winter before we realize A, we need to figure out what backpropagation is going to do for us, and B, we can't solve non-linear problems. We can only draw linear hyperplanes with these things, and we're actually going to, I'm actually just going to show you that. It's the best way to show you that. So has anyone had experience with sklearn at all? And sorry, I just realized my chat box is in the way. I do apologize. I'm going to put it in this little corner. Yes, of course. So a lot of you guys who've dabbled with machine learning, you know all about sklearn, right? The closest we're going to get to a perceptron in terms of easy deployment right now is using sklearn. So if you run this, we'll get our logic gates. And if you run this, we will get our perceptron. And I just wanted to give you guys a really easy machine learning classic example of a nonlinear classifier in a random forest classifier. And what we're going to see is we're going to see the shape of inference, or the shape of kind of prediction. This is the way I chose to show you guys how neural networks really work, because for me, it's the way they kind of draw those predictions that really make them so different. So all I've basically done is, we're dealing with our data, right, is 0001, 1011. I've just padded the data out just so we can see it better. And we're just gonna draw a contour plot, and then we're gonna draw color-based the prediction. So let's just have a look at that. And I've just made it a little bit interactive. So has anyone experienced IPy widgets before? I'm always using them. You can do silly things with IPy widgets. So if we just run this and we run this, we're actually going to be able to just jump around all of our models using this function. So don't worry too much about this. This is just helping us visualize our deep learning models later on in the game. So you should have two drop downs now, right? They're not doing anything. What's happening is this widget is just observing, and then we're just going to clear our output every time. So I'm going to leave it on perceptron, right? So if we have a look at the right? Perceptron deals with it really well, super easy, linear, hyperplane, easily done. We can separate our classes, no problem whatsoever. And it's worth bearing in mind, actually, let's just jump back a little bit, that we've got a learning rate of 0.1. Now, what I mean by a learning rate is, to get to this hyperplane, our update rule is really, really simple with the perceptron. It's a little bit more complicated with deep learning, but the update rule is basically what we should be observing and what we have observed subtracted from each other, multiplied by the learning rate, multiplied by the input. And so basically, we're just going to keep cycling through until the observed and what we've actually predicted are subtracted from each other, and we get 0. Basically, we just don't need to update it anymore. It's super, super simple. And it can also handle OR, right? But if only one of our inputs is on, if only one of our inputs is true, ain't happening. It can't do it. No matter how much we train it, it's not going to happen. And these guys, I think it was in McCulloch and Pitts, I always forget their names, came along and they were like, we got you with the exclusive OR. And so we had to start thinking about more complex ways of building perceptrons on top of each other and linking them together. And that was the dawn of the multi-layer perceptron, right? And we've already mentioned that the hidden layer gives us that shallow network, right? So once we have all these fully connected weights, we can start drawing more complex shapes. We can start doing more complex things. With this problem, we've only got 2 inputs, right? But we can smash a 2D image down into a 1D vector, and we can put it sideways through the network, and we can predict really simple classes with images. We'll look at more complex versions afterwards, but basically, actually, can anyone tell me about backpropagation? Do they know much about backpropagation? What's the story with backpropagation? We don't have to talk about it.
Yeah, the error gradient is fed back through the network from all the way to the end, to the back, and then it's carried back again.
Yeah, that's exactly it. It's we have a forward pass through our network, just like that, and then the cost function, and then we carry that error back through with the chain rule. The gradient of the cost function with regards to every single one of the weights and the outputs. So you can imagine, if it's a really complex network, there's a lot of operations there, which is hence why we need the graphics cards there. But we'll leave it at that so we can kind of just push on through this notebook. So what we're going to do is we're just going to look at how easy the control flow right now is for TensorFlow 2. Does anyone have any experience with TensorFlow 1? Can you tell me how easy it was for you? There was a lot of boilerplate code. you had to define sessions and global variables, and there was a lot going on. You had to predefine your computational graph. I think in the later versions, they started adding autographing and so on. But the great thing about TensorFlow and the TensorFlow 2, and the thing I'm really excited about, and then one of the things that makes people really excited about the other APIs like PyTorch and so on, is the dynamic control flow, the Pythonic control flow, the fact that there's just immediate default eager execution. So we can verify operations immediately without a predefined graph at the cost of a little bit of time. But we'll have a look how to switch in and out of that in a second. So if we run this now, we can just do it without any graphs or anything. And we can just print our tensor. I've actually just added S there for some reason, a little typo, sorry. Done. And then we can get a tensor of zeros, right? And I want to create some dummy data. Does anyone know how to, anyone have any experience with TensorFlow 2 at this point? Are you guys following along at this point? All good? And we've actually got to define our D types. Oop. My mouse is actually dying on me, so I keep getting these little typos. No problem. Oh yeah, yeah. No problem indeed. Can anyone see my syntax error here? It's here. How's everyone doing? Is everyone at this point? There's so many parentheses and everything in it. Okay, so we should have our dummy data. Then we need weights and a bias. So if you go back to here, right, we need to add a weights matrix. So we got our dummy data. Let's have a look at it, in fact.
Hey, can you also discuss a little bit about the weight values, as in suppose if some weight values are so high and some weight values are so low, then what it means essentially in terms of the analysis of the overall model from the data point of view itself?
If the weights are super, so the weights get, the weights aren't just, they get randomly initialized according to, there's a uniform initialization, and there's a HE uniform initialization, and they're essentially optimized for different situations. So you won't find yourself in just a random situation where your weights are massive, you know? And there's obviously operations that we'll get involved in later on in our exploration, where we'll we'll normalize our data to, like, for instance, if we're dealing with images, we're gonna, and you know, they're usually discrete pixel intensities between 0 and 255, right? we'll normalize that to be between 0 and 1, so it helps with that computation. So the neural network isn't lost in the wild, like, oh no, I got massive updates to do, if you know what I mean. How are we doing it? So we want our inputs to be 1024 long, right? Because we got our dummy data as just a 1024 1D dimension. I'm trying to keep it slow for you guys, so I'm not just like typing like a madman.
So do we have to always initialize the weights and biases, or like this is just an example?
No, I'm just, what I'm going to do is I'm basically creating a dummy situation for you guys to show you guys the efficiency of the TF function decorator. I'm trying to talk and do this at the same time. But we're going to stay high level. But I want to show you something. I just want to show you the difference in speed. Can you guys finish this off for me for the bias? And I'm just going to add a seed again. Right? So if we think about what was happening with the perceptron, right? We're just weighted input. We're going to want to do that, right? We're going to want to create our own kind of custom function, and we're going to want to add a bias. So let's do the vanilla version of what that might be. So what I'm going to ask you guys to do, and I've given you some hints here, and just to go back to that question, why are we doing this? We're just creating dummy data, and I kind of want to get you a low level understanding of some of the operations that are happening in a forward pass before we just go crazy through the high level API, which is so much easier. So I'm going to give you guys a second to do. I originally wanted to get you guys to decorate with the autograph function, but let's do the vanilla version of what you think a forward pass is in a neural network. So a weighted input. And again, I've given you this function already, TF mapmo, to give you a kind of understanding. And don't worry if not, we've got our solutions, and I'm here, and I'll slowly do the same. Just want to give you guys a couple of seconds to try and do some detective work. And I'll give you, again, I'll get you started. To decorate it, and it's really handy. But then we want to start defining our functions, right? So we're going to want an add. I'll leave you at that for now. And we're going to see why I'm doing that in a second. Okay. Super simple. Oop. This is my failing mouse again there. Let's do it again. And now you're going to want your matrix multiplication situation. So let's call it a dense layer. It's what we deal a lot with in our matrix multiplication, a dense layer, fully connected. And then let's go X. And let's go weights, and let's go bias. And then about the matrix multiplication part. Oh, let's doing it again. And then what's missing? So we've got our weighted inputs.
The bias.
There you go, done. Nice. Cool. So we've worked pretty low level so far. We got a little bit of an understanding, right? So vanilla, we're just going to do the same again because I basically want to show you the difference. I've actually already got it set up for you guys here. So I hope everyone's gotten this far. Vanilla makes me want ice cream every time I smell vanilla. Right, so we got our multiplication, 387 ms. Dense layer vanilla is not defined. Oh, apologize. We should actually add a bit of vanilla. Faster. So what's happening is at the expense of eager execution, we lose a little bit of time. But we can, on the fly, we can autograph, we can define graphs as we go. Just wanted you guys to get, Discord is always popping up in my life. I just wanted you guys to get an understanding of how easy the dynamic control flow is on a low level, but let's go up to high level. Or in fact, first of all, let's have a look at it. So before we actually do move along to high level, we've done the weighted input, right? We've done the matrix multiplication with our weight, and then we've added a bias. What's happening here? What kind of activation are before we were looking at the heave side function, right? Does anyone know what kind of activation, non-linear activation function is being used nowadays in really deep networks? Oh, I've given you the answer, silly Rhys.
Is it ReLU?
Sorry?
Is it ReLU?
It's ReLU indeed. Who is that?
It's me, Malik Malikovsky.
How you doing, man? Can you tell me?
I'm doing well. How are you?
More about... I'm doing well. Can you tell me a bit more about it?
Okay, so basically, it doesn't when it goes into the negative, like it's just a small, and then it's not a zero, right? It's not a zero, right? Yeah. That's exactly what's happening. So let me just run these. Sorry, I'm trying to switch my computer because my battery is being silly. So yeah, basically what's happening is with our rectified linear unit is exactly what you were saying there, is we've got our weighted input coming to an activation function, right? And that's exactly what's happening. If it's below 0, it's switching off. And if not, carrying on. Now, the reason we use, does anyone know why we use rectified linear units? So we know what a rectified linear unit is. Does anyone know why we use rectified?
Yeah, so what I understand in this case is ReLU avoids vanishing gradient. So at the several steps of back propagation, the model will learn to assign better weights, and that's what we need. So the whole agenda is at every step the model should be able to learn something, and ReLU helps with that, because on the permitted sides the numbers can be anything.
Yeah, that's it. That's it. Yeah, you got it. It's good to know that people have. It's great that you've made these expressions. I'm sorry if I'm freezing a little. I'm having a little issue with my battery there. But yeah, that's exactly it. And on top of that, one of the reasons we use rectified linear units is it's computationally efficient as well, in the sense that on this side, the derivative is always 1, right? And the derivative on this side is always 0. So it's a super simple thing to stack on top of each other in terms of like layers upon layers. And then on top of that, we get the benefit of avoiding the vanishing gradient issue if weights are being, if the weights are tiny little updates, then with the learning gets slower and slower. So talking about the vanishing in gradient situation, sigmoid is going to do that for you if you're stacking those, but we're going to use sigmoid. And does anyone know why we're going to use sigmoid for this specific problem?
Because it's a classification, a binary classification problem.
Yeah, right. It's that's exactly it. It's a binary classification problem. Our input basically gets squashed between, yeah, Chai, you've got it as well, because it gets squashed between 0 and 1 basically. So we've got a probability distribution. Isn't it, I believe, a Bernoulli distribution? That Swiss guy. Am I getting that right? Bernoulli? Yeah, it's Bernoulli. So the probability distribution or the distribution that basically gives us the closest we get to 1, the closer we get to the true class or the positive class of our problem, just like that. Okay, so rectified linear unit. So let's actually move on and let's create our first neural network. So I've actually sorted this out for you guys already. I forgot to take this out, but I've already taken a few out for you guys so you can do the rest. So let's go high level and show you how easy it is to like build the building blocks of a neural network, right? So we've got our exclusive OR gate. We know it's a problem for us with the perceptron. And with TensorFlow 2 now, all you've got to do is pull in the Keras level API, and you're flying with those building blocks quite easy. It's now become the official high-level API. They were separate at one point, but now it's just fully integrated and super easy for those of you guys who don't know much about this yet to just feel like deep learning superheroes. So we're going to stick with the sequential API this time. And what we're actually going to do is kind of what we were doing already, right? Where on a low level, we had this matrix multiplication weighted inputs to our activation function. But all we've got to do now is we just got to go mlp.add, and I'm going to get you guys to do this in a second. And then we're just going to add a dense layer. And then here we're just going to have 16 nodes on our hidden. And our input dimension is going to be 2 because it's a binary problem, right? We've just got that gate coming through. And our activation is the rectified linear unit, which is done automatically for us. It's available as a part to just use. Now, why am I saying dense 1? I'm saying dense 1 because simply, like I said, it's a Bernoulli distribution, right? So all we're going to get is an output that's, sorry, it's the last layer and you just want one. Yeah, sorry, Chai. I realized that other people are actually talking on this side as well. That's exactly it. We just want a prediction between 0 and 1. We just want a probability distribution between 0 and 1. So let's go ahead and compile that. And we're compiling it with binary cross entropy. Now, the reason we're doing binary cross entropy is because it's a binary problem. And also at the core of binary cross entropy is basically the negative log of the probability that it's the true class, right? So the closer we get to 1, or the closer we get to it being the true class, it exponentially loses, the loss exponentially drops, basically. So that's why does comment state that it is broken? Oh, sorry, because I do apologize. This was I did break it. And I meant to have it gone for you guys, but unfortunately I've left it in for you. So that's why. So let's get rid of that. Well caught out there, Caleb. So again, at the core of binary cross entropy is the negative log of the probability that it is the positive class. And that just helps us get that kind of exponential drop with the loss. So let's compile it. It isn't broken, and we're going to use stochastic gradient descent because we're just putting one data point through it because it's not a very complex problem, right? And let's we're going to switch off our verbosity because it's going to smash through loads of epochs really quick and it'll clog up our notebook. The cardinality is ambiguous. I wonder why. Is everyone getting the same problem?
Yes.
Yes.
I'm getting it too.
I wonder why. Apologies there, guys. Sometimes these things happen. Oh, there you go. So if you run X, oh no.
Maybe because Y is an array of 4, and it is expecting maybe like 1 by 4 or something like that.
All right, I'll debug that in a bit when I get you guys to move on to the next exercise. But basically what we would end up having, is a prediction that was super complex. We could draw all kinds of crazy shapes with the rectified linear unit, in the sense that we're getting non-linear output, right? So instead of, if we go back to our random forest classifier, it's also non-linear. But if we switch, we notice that because it's kind of an arborescence, right? Yes, no's, and so on. We're going to get decision boundaries that are 90 degrees to the X and the Y. So if we switch between all of these, we can classify every single one of them, and we can even classify the non-linear gate, but we're not going to get the benefit of the complexity of a neural network in that sense, which is what we're seeing here down below. So let's actually have a look at another data set, and let's get you guys to do exactly the same thing. And I'm going to have a look at my situation in a second. So I provided you with a data set, which is also a binary problem. And you should end up with something like this. But again, because it's a Bernoulli a distribution, you're going to get this lovely little granular situation where the closer we're getting to our class, the contour plot's going to show us that spreading of prediction, and we can switch that on and off. What I'm going to ask you to do is to emulate what I did there with the input dimensions. This should work with the sequential model here. So code away, and I'm going to have a look at what's going on. So I'm going to give you 5 or 10 minutes, and we'll do the same together in a second. You will be able to switch between positive trust for that particular problem there. So again, the solutions notebook comes to save the day there. Yeah, for sure, Ashton. Yeah, with the if we do with the low level situation, that's your solution there. With the high level, do head over to your solutions notebook. And then you should be able to, so let's have a look. So while you guys are coding away, how are you all getting on? Has anyone completed it yet? Let's have a look. It may actually be the optimizer. No, oh, very strange. So if you have a look, we've properly authorization code. There shouldn't be an authorization code there, Caesar. So if you head to your solutions notebooks and have a look at this. You'll see we got our exclusive OR. Now, depending on how many epochs we run, how many what optimizer we use, we're going to get a different kind of shape. Cool, huh? And we got there in the end, which is wonderful. Now, what I mean by optimizer is we were looking at stochastic gradient descent earlier, right? Which is nice and simple. I'm glad that worked out for you there, Caesar. There are obviously other more previous steps learning rate to just get this idea of a lot of people talk about a ball rolling down a hill. That's exactly what's happening. We're getting that kind of momentum where we're pushing quickly to the negative gradient down to a local optima. Now, obviously, you know, we've got more than one, we've got more than two parameters. We've got thousands of parameters in this situation. So we're talking about a high dimensional, but neural networks are still great at dealing with these gradients, and we can use advanced optimizers to do that. Yeah, so you should have solved that, and you should be able to solve the same problem with something very similar. Has anyone gotten this far? Yes. Did you get it, Albina? Did it work? It looks similar to mine. That's great. And again, we're going to use binary cross entropy, right? Does anyone else need a little bit of time? Yes, yes, yes. It looks similar to mine. Great. Get that kind of, we show the real complexity of a neural network in in using those nonlinear activations to navigate the situation, right? I'm gonna give you guys a little bit more time in case some of you are still working on the problem. Does it? Couple more minutes, guys. Has anyone had any experience with the functional API? So we looked at something very sequential, right? Can anyone tell me how I start off with the, it's all very intuitive. What's my shape here again? It's going to be 2, right? And now instead of looking at, instead of doing the whole model.add, you just do things functionally. And what it means is using reusable parts and right? Can anyone finish this part? Let's do this together. What's my activation? Let's do relu again. But instead, we just whack our input at the end, right? What do I mean by functional API? So I'm showing you the functional API here, basically. So with the sequential API, we're basically just adding our layers. We're adding our dense layer, our fully connected layer, and then we're just adding, it's just a different way of doing things, basically. And we're just adding our sigmoid output to get us that kind of 0 and 1 output. With the functional API, it's just a little bit of a different way of dealing with things. But what it means is that when models get more complex, we can start reusing parts. The more you go down the TensorFlow 2 road, the more that you realize that it's super helpful to you to be able to reuse parts. And can anyone tell me what this would be? So instead of putting our layers in that model add parentheses, we can just do them on the fly like this. A lot of people find this a lot more intuitive. Can anyone finish this for me? Right? How about the next part? So given that our input, we're just putting it in parentheses at the end with the functional API, what needs to happen here? Dense, you got it. Nice one. And then what's the rest? Anyone have any idea what this might be? And then I'm gonna do this part here. Why dense? The naming convention can be whatever you want it to be. I'm saying dense because it's a fully connected layer that we're using. I would say, for instance, I would say conv, or I would say, oh, thank you. I'm always stumbling over myself while I'm talking and coding at the same time. Yeah, so it's just a naming convention for me. I could actually, if I really wanted as well, I could do X. It doesn't matter. It's just easier to keep track of the more sorry, that would be input. And then we could have XX here. Spelling mistakes. Thank you, Mohammed. You guys are experts already. So you see what I'm saying? It doesn't really matter what you call it. All right, what goes in here? You got it. Input. Done, just like that. And then we can just compile the same way as we did before, right? You guys got this part reusable, ready to go? This should actually be underscore, sorry. And what do we want to use for an optimizer? Let's use, oh, I do apologize. Right? You see how it's auto-correcting for me anyway? What's next, guys? What's our loss? Let's go binary again, right? What about our metrics? We're not actually using metrics at this point, but we'll have a look at it later on. How about the next part? Let's get our history. And then after this, I'll probably switch over to the next notebook. Anyone care to finish this for me? Right, we're just gonna fit it. And then our data is XY, right? We don't have a train and validation set right now. Fit, yeah, great. Well done, Albina. And then epochs. Can anyone tell me what epochs is? Aria, so in this way, maybe we can connect to like SQL. Yeah, it's a lot easier to throw in custom architecture for sure. And yes, the number of passes we go over, that's exactly it. And let's go for 64 for a batch size. And let's just have our verbosity at 1. Trying to keep it nice and slow for you guys. And then let's just validation split at 0.2. Am I missing anything? What's wrong? Classic spelling mistakes. What's wrong again? We're missing fit, right? Oh, sorry. We're missing compile. And lots of spelling mistakes. This is the story of my life. Always spelling mistakes.
I think it's X train, Y train.
And batch size. Oh yeah, sorry. There you go. Problem solving together. Wonderfully done. And we got it. And then if we just whack this in again, a little image, and then we can switch off to our classes. Right. So we can actually solve a lot of problems with just this kind of architecture. How do we read the output image? So like I said beforehand, what's happening is we're getting, because the output node is a sigmoid, right? So we're squashing all our inputs in the sigmoid into a 0 and 1 probability distribution, a Bernoulli distribution. So we're basically pushing to the positive class. So we're just getting, we're seeing the result of that distribution here. So we're just plotting. So for every single point in this plot, we're just saying, is this class or not? Is this the positive class or is it the negative class? So the darker it is, we know it's definitely not the positive class, right? And then the closer we get to our positive class, the lighter it's becoming. So this is a good way of plotting without having to plot hyperplanes and so on. We're getting the decision boundary that way. That's how you read this plot. And this is a really good way of looking at kind of those binary distributions. So we can actually, like I said, we can actually solve a lot of problems with this kind of architecture, with just a fully connected architecture. We can even solve image problems. So does anyone know about, has anyone come across MNIST before? It comes up all the time with these kind of problems, even in standard kind of machine learning. Yes, Albina and Caesar and Angola, yeah. I'm going to get you guys to solve this because I think you've probably got the tools to do it now. We're pretty much going to emulate the same kind of architecture and maybe tweak it a little bit, add some more nodes, maybe add an extra layer. So go ahead and import your XY train. Remember this time, like I didn't, that it's that we split it into our validation and training data sets. And then if we actually just look at the actual array itself, like we were talking about earlier, images are between 0 and 255 in terms of pixel intensity. So if you think of images this way, it's really handy in dealing with neural networks and dealing with the idea of high dimensional data. Now, can anyone tell me why they think images are high dimensional? Why am I calling them high dimensional? They're 2D, right?
There's also arrays for the colors.
Yeah, yeah, for sure. That's a good. There's also a there's a channel, right? Color images are more than 2D. Yeah, for sure. There's a third channel, RGB. But you can also think in terms of so to finish that picture and to finish that idea, if we plot the Inception poster, me being the Christopher Nolan fan I am, this is going to take forever actually for us to see it. So I'm not going to run this function because it takes so long. And for me even to rotate the axes, it takes forever. But let's also plot MNIST. And feel free to actually switch your data here. So let's try all the different ones. With MNIST, it will be able to deal with it a lot better. So run this guy. And we should have made an interactive widget this time, right? It would have made it a lot easier to switch between all the different training but let's we can actually have a look. We can rotate. So what we're seeing here, a good way of thinking about images is that they are discrete pixel intensities, right? So the lighter the color of the pixel, the higher up it is in the 3D plot, right? And we've got the darker here. So we see these big valleys. So in terms of computer vision, or in terms of the idea of thinking about images, we want to figure out what these sharp drops are, right? These kind of like gradients are between those pixel intensities. And a way to do it in classic computer vision is obviously to get like an approximator, an edge filter, a convolutional filter, and we convolve the image that way, and then we approximate that image gradient, right? Classic 101 computer vision. But we can actually solve this with a just standard dense architecture. So I want you guys to, first of all, tell me what I need to do to get this supposedly complex image into a standard dense network. And I'm going to go right back up to my picture. Sorry about the jumping around, guys. What do I need to do to get it into here? First of all, actually, before we do that, it's worth thinking about, remember we were talking earlier, we had a great question about putting through massive weights or massive updates. What's the first thing we should do? We should normalize our images, right? So how do we go about doing that? Anyone got an answer? What about the test images? Oh yeah, sorry. We need to flatten it for sure. That's the answer to the first one. Now you can do it in two ways. You could do either a flattened layer, or you can do it really manually if you wanted. How about the reshaping? How do we go about doing that? We need to just drop an axis, right? How would we go about dropping an axis? I'm going to check the chat.
I have a question.
Yeah, go ahead.
Why do we normalize or reshape our image?
Sorry?
And why do we normalize or reshape our image?
So like we were saying earlier, it's just more computationally efficient. So now we've done it. What do you think the output of? What do you think the output of the first image is? It's between 0 and 1, right? It just makes it computationally more efficient instead of putting just massive images through. Think about as well, if we had like really high resolution images as well. Normalizing helps us with that kind of computational efficiency there. So what's left here? So we've seen that our X-train is 28 by 28, right? These MNIST are easy to deal with because they're really low res. 28 by 28 is cool, and let's do exactly the same. I'm a copy and paster. I don't know about you guys. Okay, and now you guys should have everything you need to emulate that same problem. So I'm going to get you guys to solve this with that architecture again. So with a dense and then a sigmoid. Oh, sorry, no, I'm actually wrong this time. Why am I wrong? What do we know about the S1? Because we're just dropping, we're dropping one of the axes. Why am I wrong about a sigmoid? I'm getting ahead of myself.
Because we have multiple classes.
That's it, you got it. There are multiple classes, right? So what are we gonna need to finish our, so when you guys are coding in a second, what are you gonna need? So you're gonna need the dense, you're gonna need your input, but what's gonna be the output? It's a multi-class situation, isn't it? So with a multi-class situation, we're gonna want a soft max output. So our dense output is going to be, there are 10 classes, aren't there? So we're going to want to change our activation to softmax at the end there. And what softmax does there is you basically, the inputs, the current input, the exponential of that, it's the ratio between the exponential of that input and then the exponential of the sum of the other inputs. So we're getting a probability distribution again. We're kind of pushing them away from each other. So you're getting probabilities between 0 and 1, but then you're getting the specific class, the probability of the specific class that our neural network thinks it is. And we'll have a look at that in a second. So try and emulate that. Let's try and do what we did with binary, but then let's switch dense to 10. And then let's switch our activation to softmax. And I want to get you guys involved in that just so you feel like superheroes. I'm actually going to switch to solutions because we've still got quite a lot to do. And I want to show you guys a little bit more. So I'm going to give you guys about 5 or 10 minutes again. So remember, we're doing exactly the same thing with our data. And we're just switching the output to softmax activation because we want the ratio between the exponential of the input and the sum of the exponential of the rest. And I'm just gonna rerun all of this so we can get through everything I've got left. And again, I know it may very well be a lot to take in, but you've got your solutions notebook and you'll have those to knock through again when you need them. And I'll recap what I think that you guys should take away from this also. I debugged the hell out of this solutions notebook. So everything. So I'll give you guys a couple of minutes more while I import my data. So far you should have your I'm not going to import this because we haven't mounted. We should have a rectified linear unit in your first hidden layer. And then you should have a soft max output. Just going to run this. And we're going to use one of those momentum-based optimizers we were talking about. Remember the idea that we're going to add, and we're going to use the defaults on this, but we're just going to add the learning rate from the previous step as we go. And this time we're going to use sparse categorical cross-entropy. And categorical cross-entropy or binary cross-entropy is a special case of categorical cross-entropy. Can anyone tell me why I'm using sparse categorical cross-entropy here? And how are you guys getting on at this point? Has anyone solved the problem yet? So the reason we're using sparse categorical cross-entropy is because these classes are, while you might think numerically speaking, there might be a relationship, right? If we were just dealing with 0 to 10, it's handwriting, isn't it? So we need to one-hot encode our categories. We could manually one-hot encode by just importing an encoder and then 1, 0, so on and so forth for 10 of them. And all the way to and then the 1, all the way up to 10 classes. But sparse categorical cross-entropy, but it does the encoding for us. So we're one-hot encoded. So are we at this point yet? In your notebooks, have you run this? And have you compiled? I haven't seen anything in the chat, so I'll give you guys a little bit more time. There's no rush whatsoever. We have everything ready in front of us now.
I have a quick question.
Yeah, for sure.
How do we choose the input dimension in the input layer? Like, if I'm doing something, how do I choose it, the input dimension?
So that's a good question. It's actually if you think about the number of nodes in your hidden layers as hyperparameters. So it's actually a matter of just tuning There are obviously ways of doing things nowadays, like kind of grid searches like you would classically with old school machine learning algorithms to tune or to, and in fact, we're starting to develop ideas now where you can do things like neural architecture searches where you can find the right base architecture for your neural network to get started with, especially with the more complex neural networks. But at this point, the way we're dealing with it and the way we're kind of investigating it, it's literally a matter of tuning for you. So if you think about the more nodes you add, the more complex it becomes. So we're trying to kind of shape the network to the data. So if we wanted to deal with really complex images, we would add more nodes and we would add more hidden layers. Or in fact, we would add convolutional layers, which is what we'll have a look at in a bit. But yeah, it's just another hyperparameter for you to tune. And so is your signal break off a bit when you explain sparse categorical. Okay, I'll get to that in a second. But yeah, so for you right now, it's a matter of playing while you're getting used to it. But there is an intuition in the sense that if we go back to the original problem with the really simple data, you don't want a complex network. You don't want to say, for instance, 64 nodes in your hidden layer. It's completely computationally redundant to do so, right? So yeah, have a play around with that. And you could probably actually get rid of some of these nodes and still solve this problem. In terms of the sparse categorical entropy, just to try to reiterate on it, like I said, binary cross entropy is a special instance of categorical cross entropy, right? And we could use categorical cross entropy in this situation, but we're not dealing with related things here. We're dealing with handwriting, so they're kind of separate from each other, right? So we'd want to hot encode our categories. Sparse categorical cross entropy just does that for us. It deals with them one hot encoded. So it's super simple that way, done and dusted. Now, what I'm going to do is, let me just mount this because I want to start showing you guys checkpoints. Checkpoints are really, sorry, not checkpoints, callbacks, because callbacks are really exciting to me, because callbacks for me are the really create, because I just want to show you the different things you can do. Okay, so I'm assuming that a lot of you got to where you've gotten, or if not, you've got your solutions notebook. Like I said, we're running out of time. At this point, you should have your network, and I've added an extra layer here, and we've added softmax for the reason that we have 10 classes, right? And we've added sparse categorical cross entropy because we need to one hot encode. What I'm also going to do here, and what I would ask you guys to do to add to yours, and I'll give you guys a couple of minutes, but we'll move on quite quickly given the time, is to use these callbacks. So the beauty of Keras as a high-level API is we can start adding in different things to deal with our training, or to kind of pseudo-regularize while we're working with our data. What I've got here is, can anyone tell me what they think early stopping is as a callback? It kind of does what it says on the tin, but has anyone experienced the idea of early stopping? They may have with sklearn, in fact.
Oh, the whole idea is like it stops it before it opens.
Yeah, that's exactly it. Yeah, and it does, and we got an answer here about preventing overfit as well. Yeah, we basically, you see, I've got it set to monitor the validation loss here. You can actually change it to whatever you want in that sense, and we've got it to set it to a minimum validation loss, and we can also change this patience here. So if we're dealing with some really complex data, something really complex, and we know for certain that it's going to have trouble updating the weights at some point. You know, we want with the back propagation with the gradient descent, we want to get to our local, our global minimum, our minima. We have an inkling in our minds that it may get stuck at some kind of local minima somewhere. To deal with that, we can actually switch our patience or change our patience to something a little bit higher, maybe 10 or 20. And basically, we're then controlling how long it stalls in that, to give it a chance to kind of maybe push down to that global minima. So it's worth bearing that in mind once you start getting more complex with this, that this is a hyperparameter that you can change, and is a hyperparameter you should change if you know that you're dealing with data that is that complex. The other thing I've got is a model checkpoint callback. Now, the great thing about a model checkpoint callback, and the great thing about TensorFlow 2 in general, is they've moved away from frozen inference graphs. Now, frozen inference graphs had everything kind of fused in it. They were difficult to deploy sometimes in terms of having to go through this whole freezing process. But now a lot of variables and weights and so on are saved into separate assets and can be loaded quite quickly. You'll see this when you're dealing with the entire ecosystem, like TensorFlow Hub. You can bring in a part and then load the save model quite easy. Or even if you're dealing with other toolkits for deployment, like OpenVINO, which is what we'll be looking at next session, you can take a save model, you can optimize it, you can take away what you need, and you can deploy it as a really efficient model. And this new kind of method of doing things helps us do that. And we can save our checkpoints. And you can see that some of my parameters here, I've just got it to just save the best. And I've also got it to also monitor the validation loss. So let's actually just, we should have already done this. And let's look at that in practice. Now, this isn't a very complex problem, so it should actually deal with it quite quickly. And again, we got a batch size, and you notice in our fit, we've actually, when we're calling fit, we've put our callbacks here in a list. And this can be really common. We can have loads. We can have, and we'll have a look at TensorBoard in a bit. You can see I'm writing my assets now to Google Drive. We could be in the cloud. We could be on a cloud machine. We could be writing to a bucket. And we could walk away and work on something else. And then it's available for us to deploy or to verify the way we need or the way we want.
Could you explain callbacks again with also like what was ESMS? I got confused.
We'll actually, yeah, no problem. We'll actually look at more complex callbacks in a second as well. So what's happening with callbacks is we were just grabbing our early stopping callback from Keras, the API, which is a intuitive, tf.keras, the callbacks. Not only help it if we do need to push it over the edge to a global minima, but it just helps us not basically smash in 500 epochs and it trains for 500 epochs and it doesn't need to. It's time intensive, resource intensive. It gives us that kind of pseudo automation, right? And then the model checkpoint, what the model checkpoint is doing is it's just monitoring in a similar fashion to early stopping, but we're saving our model for reloading. So we can walk away, we can do something really complex and go and work on another problem while this is saving to a local machine or to a virtual machine. And then literally all we do is we whack them in our fit call. And then you'll see at the bottom here, it's stopped at 20 epochs for me instead of running at 300. And then I should have a model saved to Google Drive ready for either deployment or verification. And we'll actually have a look at that now. We'll skip the functional because we've already seen that. It's a very similar idea, but we've just added softmax and we've just added the output of 10. Hey, no problem, Yasmin. Thanks for speaking up. And again, we were talking about the syntax of this, right? I've just added X's because it doesn't matter to me in this point. If I want to keep track of a really dense, really deep, complex model, then I'm going to want to have better naming conventions, but I can just use X if I wanted to. So let's actually have a look. You notice that every time we haven't seen this yet, we've been fitting to our history variable. Well, we have our metrics dictionary, so we can actually just plot that. And you guys might have seen this in classic machine learning. I need to actually some of us have written that a million times. And then accuracy, I believe, I wonder what is going on. I think it's actually ACK. Cool, and then we can just on the fly, we can actually, but we're actually gonna move to another callback that does this on the fly for us, so we don't have to just whacking code manually like this. So first of all, let's have a look at the result of our checkpointing and our early stop. Stopping is just load my model, and then I can grab my predictions. So I just need to import NumPy, if you bear me 1 second. So in terms of day-to-day life as someone who's dealing with deep learning and is wanting to jump around all the problems, like I said, you can just run stuff in the cloud, run away and come back. I'm just grabbing my class names and then I'm going to look at my predictions. 7, but there are more complex ways of verifying our data, and we're going to have a look at that now. First of all, I'm going to plot them all, but I really want to show you a really, really, really cool callback that's really going to get you intuition of how a little bit dark, so you can't see these labels very well. I try to work with the dark one because of my eyes, but do speak up if you can't see these. But yeah, so you can see it's done pretty well with only 20 epochs, and thanks to our overfitting, we've gotten this far, right? What I want to show you now is we're going to do exactly the same thing. So I need to get show frame, if you bear me 1 second. It's just another Keras data set that's available to you, a TensorFlow data set. And it's basically images that are a little bit more complex. So I've gets our predictions, and I'm going to plot it epoch by epoch. And this should actually be, if you bear me 1 second, it should be Sifa. Solutions this time because the data is a little bit more complex, and I'll talk about that in a second. We'll actually look at a video of a more complex version of this in a second, and I'll explain what I mean by convolutions. So let me just compile this, and let's actually change this to see how many parameters there are. You can see how much more complex neural networks are in terms of weights and activations and so on. And you can see that I've still got my, my softmax at the end there, right? So the convolutions, and we'll discuss it in a second, we don't flatten. We flatten at this point. So this is a special kind of operation. Flattening does exactly what we were doing when we were dropping an axis, and then we can put it into another fully connected architecture like we were talking about earlier. You guys are familiar with this dense 128. I probably don't need 128 nodes, right? It's not that complex a problem. And then you are fully familiar with this idea, and you're fully familiar with sparse categorical cross entropy. But if we run this with these callbacks now, so we have ES, early stopping, we have a lambda callback. Lambda callbacks is what I want to show you right now. So I should have TensorBoard loaded, so I don't have to worry about plotting anymore. It's going to do it in TensorBoard for me. And we'll have a look at that now. It'll take a little bit of time. Which I think for some reason, things like plotting projections of images and so on there. But so what a lambda callback, it's basically one forward pass through our data, right? So at the end of an epoch with our lambda callback, we can actually execute a function. So we can start doing crazy things in between our training to really get an intuition of what we're dealing with. That works really well for things like generative artificial networks that are trying to map one idea to another idea with image pairs. And you can start to see, I call them the creative AIs, right? You can start seeing their creativity epoch by epoch to see if you've got the right kind of hyperparameters or the right architecture on the go. So I'm actually going to show you that with this right now. So we're going to plot epoch by epoch. And you're actually not going to see that much of a difference in the sense that, okay. C to 0. what you should see then is your inference. Deer, frog. I think we've got them all. We're doing pretty well, right? It's not a really complex problem. So we're not actually seeing gives you an intuition of how Lambda callbacks work. What I'm going to actually show you now is a manifestation of that with something a little bit more complex, right? So what I did before this, here's something I made earlier, is first of all, I wanted to show you how easy it is to use reusable parts. Jai, yes, of course I can turn off my video, no problem. Is you can actually fine tune models. So convolutional neural networks, you can just grab them on the fly, and then you can, if you have a look here, I've taken away the top layer so we can add our own kind of dense layer. I'm not actually going to show it to you this time. And the weights, I had none this time because I wanted to unfreeze every single layer of the architecture. So you can see with VGG16, I wanted to use VGG16 because you've got blocks of convolutions and it's easier for me to show you the this video. But basically what convolutions do, and we'll see it in a bit. So this would be ImageNet, which is the data set it was trained on, if we didn't want to unfreeze it. Let me actually show you the video first. Right? So every frame is an epoch. And I've added every layer sequentially in this video. And I'm doing this all programmatically with code with the Lambda callback. So the Lambda callback is plotting. It's taking that frame and then it's adding it to a video. So you start to see the complexity of what we can do with these kind of APIs, right? So we're falling down through the layers of a convolutional neural network. At the start, you see it's just randomly initialized weights. And those are kind of an analog to edge detectors, to Sobel filters. What they're doing is they're taking like a 3x3 kernel and then using that anchor pixel and then convolving pixel by pixel to find an approximation of those image gradients, to find edges and so on. But then as we fall down the layers to the pooling, we're smashing down, we're downsampling so we can find the abstract, more complex things that are translation invariant. Because one of the things that we're looking for, and one of the things that make neural networks so complex is the fact that not only can we classify an image in itself, but we can also take an object in an image and we can find that anywhere. So we can find a dog in the distance, or we can find a dog's ear somewhere. Translation invariance is found through this kind of idea. These aren't fully connected. Those convolutions have their own kind of rectina, and then the downpooling finds that translation invariant idea, and then we get more and more and more and more complex until we end up at a softmax a layer again, and we end up at that probability distribution for those categories again. And this is all done with what you just saw. So you guys now have the tools to do what I just did. You have the tools to start making really, really, really complex ideas, right? And then the last thing I will look at is, like I said, this is an entire ecosystem. And if I just grab a drink a second, bear with me 1 second. And I do hope that your signal is better now. And I do apologize in advance for those cutouts. And I'll leave this visualization of this Lambda callback for you. One of the things that makes TensorFlow so wonderful to work with, and we'll see that in the next session when we do something a little sillier, when we look at things like robots and deployments and adding our own data to all of this infrastructure, is TensorFlow Hub. If you follow this link in your own time down here, TensorFlow Hub is a complete playground of working parts. There are image classifiers like we've seen here. There are language models, there are embedding models, there are pre-trained models like BERT. I don't know whether BERT is fully supported yet. But what it means is that you can fine tune and leverage models on the fly. I'm going to show it to you right now. I'm going to show you actually using embeddings, and I'm going to plot those for you. But first of all, what we're going to do is I urge you guys to run this first. We need to I need to run my functions eagerly because this part here, the part that we're importing, I'm going to be essentially looping through with my interactive widget. And if I don't switch to eager execution, these parts are going to be imported with the TF function decorator. So they're going to be autographed. They're going to have a hard computational graph. And we're going to start getting a retracing area, and we're going to start being computationally inefficient. So let me just run that, and you can investigate this in your own time. Look at the cosine similarity, or the inner product of our embedded word vectors. So I'm going to say, it was nice to see you all. And then let's write something a little bit longer. Like science fiction. Hey, no problem, Albino. And then what else should we write? It was let's write something really negative if we're going to look for the inner product. I'm sorry, I'm going to write something really negative. You know, I'll write something about movies, because one of the things that you can do, in fact, because I'm sure there'll be questions about how do we apply this kind of stuff. One of the things that you can do with natural language processing with deep learning and with Keras and so on is to start getting involved with things like recommender systems and with text-based semantics and so on and so forth. So let's do a movie review. This movie, I wonder what movie I'm talking about. Absolutely rubbish. And I'm not spelling it properly. I don't know whether you say rubbish over on that side of the pond, but I say it all the time. So I'm going to use the universal sentence encoder. It actually takes a little bit of time. So if you bear me 1 second, it's quite a large model. I believe the dimensions are 512. I'm not too sure. I wouldn't quote me on that, but we'll have a look in a second. But like I said, the widget is observing here, and we should be downloading right now, and we should see it shortly. But in the meantime, what I will tell you guys, and what I'll give you guys a little recap. Let's actually move to one that's not so intense. I'll give you a recap in the sense that what you should be taking away from this is that TensorFlow 2 has a Pythonic control flow. So you can just knock around. Don't be scared. You don't have to worry about boilerplate code. Don't forget about the TF function situation when you're wanting that boost with your custom functions, right? Don't forget about TensorFlow Hub. Do follow these situations here with TensorFlow Object Detection API. We'll actually look at in next section. If there's some spaces for you, do jump on board. We're actually going to go through the whole procedure of, it's a shame that this isn't running. I wonder what's happening. Anyway, we will go through the whole procedure of taking your own pre-trained models, stuff like efficient net, which is a really, really complex convolutional neural network that exists now, that has leveraged neural architecture search to develop it. So another neural network has basically helped create the base architecture of that. And it's super efficient and it's got super quick inference, and it's got super good mean average precision as a kind of ratio to each other. And that's all thanks to kind of enveloping neural networks on each other. We'll look at that. We'll take our own data and then we'll put it through the ringer, and then we'll also deploy. We'll deploy on one of these guys, the sequel to this, on my end, and we'll have that control robots, but I'm going to try and get you to simulate the closest you can possible for that. We're going to actually try and get you reading frame by frame and actually detecting and tracking objects in real time. Super exciting stuff. I hope you can be there. I'm going to try and run this again. And if anyone has any questions, then I guess now's the time while we're worrying about not being able to plot.
Yeah, I'm sorry. What's the name of the class you're just for?
Sorry. Oh, it's tomorrow at 11 a.m. as has been said in the chat there, and it's deploying deep learning models to the edge, and it will be under my name.
Oh, okay. Thank you.
That's okay. Oh, it's because this part is still not running. So I'm going to try and run it again for those of you who are sticking around. What we would basically see is a heat map that shows the semantic difference between these sentences. But I've obviously gone as, oh, here we go. Is it working? One. Oh, yes, for sure. In terms of the copy of the updated notebook, that's actually the solutions notebook for you there. As you can see, if you throw a lot of stuff at the wall, it doesn't always work out the way you want. Let's just try just really simple. Has anyone got it working on their end? I believe in you. Do you know what it actually might be? If you guys bear with me 1 second, it relies on Seaborn. Factory reset this. I'm glad you guys are sticking around for the finale. All right, let's try again. And let's run let's import TensorFlow again. Let's do this. And we're gonna one last try. Enjoy the rest of the conference. I hope you guys like robots, because that's what's happening next. But yeah, again, now's the opportunity to give me a shout if there are any other questions. And like I said, it'd be great if you could come to the next session. I will. Hey. Apparently they're all very similar. Let's try another one. Let's try I know the universal sentence encoder works pretty well. It takes a little bit of time. Like I said, it's so big. But what you should see when you guys are debugging this in your own time, and in fact, you could probably just pull all of this out of the widget. What you will see is a heat map just showing those text embeddings and just showing the inner product and just showing how easy it is to pull pre-trained embeddings out of nowhere. In fact, let's do a bit of this. Instead. Yeah, I can actually explain about Lambda. If you bear with me 1 second. Let's just not plot it. So basically all you're getting. Oh, I do apologize, Michelle. So all that's happening with, once this runs, I don't know what's happening. Anyway, let's debug this another time. I do apologize about the internet. SAP. Let me go back to this. So if you think about, if we look at this architecture here, if you think about what's happening with our neural network, we're just pushing through a forward pass of the neural network, right? Through one epoch of our data set. And then all I'm doing with the Lambda callback then is interrupting the training momentarily and executing a function. And that function can be anything you want it to be. It can be your metrics. You can be plotting your metrics like we would with TensorBoard, or you could be plotting all kinds of fancy randomness like this. What I did with the activations down here was plotting. I used the functional model to plot my actual activations, and I put a single image through that activation model during the interruption of the Lambda callback. And yeah, so you can basically get as creative as you want with the Lambda callback, and it allows you to verify the actual kind of physical operations of your neural network in that sense. I seem to be having trouble with my notebook, but do feel free to run this in your own time. I'll leave it at that. It's a shame it didn't work out at the end there. No problem, Michelle. I apologize for the technical difficulties there. And I'll just knock around for a little bit for some questions. And I hope you all enjoy the rest of your summit. No problem, guys. Too many people to say by name, but thank you so much.
Is lambda and callback the same thing?
Yeah, so a lambda callback is a kind of callback, basically. Yeah.
I see. Thank you.
There are all kinds of callback sheets, no problem whatsoever, Michelle. I need to use LinkedIn more often, but I will definitely add you. Thank you for telling me. Yeah, feel free. You guys fire away with those invites. Come to the next session. It's going to be a lot of fun. You guys are going to be participating more than I am. Do I have a public repository? I actually don't. I'm super private. Because I'm always adding parts. I'm working on it though. Is it Baldemar? But yeah, it would be great to give back to the open source community in that sense. I do talk about there's plenty of silly robots knocking around.